Okay, so let's check out the ellipse, which is actually kind of a cool shape. It's kind of fun to work with. And the very first thing that I'd like to do is just kind of talk to you about what something is that makes an ellipse. Now, we talked before about the standard form, the x squared and y squared thing. And as it turns out, if the product of the coefficients on x squared and y squared is positive, meaning they're either both positive or they're both negative, that's what makes it an ellipse. Now, it begs the question, because sometimes if they're both, say, 4s, 4 and 4, their product would be positive. It's technically in an ellipse, just like a square is a rectangle. But if they're literally exactly the same thing, it's a circle. And so we might kind of write that down. If specifically A equals B, which is a very, very special case, it's a very special ellipse known as a circle. But the definition says the following, and this is a little bit of a weird definition. It's based on distances again. So I'm going to pick a random point right here. And so imagine that I played connect the dots between these two right here. That and like that. And I got a couple of distances. It's kind of a strange idea, but I just picked any two that I have right here. Let me call this one D1 and D2. And if I added D1 plus D2 together, whatever that distance is, and then maybe I picked another point, totally different value, maybe this one over here, has nothing in common with that one, and I got some other distances, maybe call this one D3 and D4. As it turns out, what happens is no matter where we go on this thing, the sum of these two would be the same as the sum of those two. And it wouldn't matter if I came to another point down here or further down here. Somehow, when you add those two distances together, you get a constant value. Now, as it turns out, that constant value is actually a specific value, and that is actually the distance between these two vertexes. Equals distance from V1, vertex 1 to vertex 2. So this is actually known as the major axis or the transverse axis. This major axis is that constant distance that we have. Now, what I wanted to do is take a look at a geometer sketch pad thing that I created to kind of demonstrate how this plays together. Somewhat complicated, but it is based on exactly what we did before. I'm going to double check and make sure that shared the way I wanted to. So what I've done is I've made a perpendicular bisector. And so just like what happened with the parabola, the distance from P to F is the same thing as from P to D. Now, the rest of the story is there's kind of a segment that goes straight from A all the way through here to D. So notice that there would be a segment that would go from A to D, and that segment A to D would be the radius of this circle. And it doesn't matter where we are on that circle. What we know is everywhere on that circle, the distance from A to D will be a constant. And that's that constant that I referred to, which is actually the diameter or the biggest difference in that thing. Now, what's weird is since A to D is constant, and here's the big kicker, since P to F is the same as P to D, that rather than going from A straight to D, it's the same thing as going from A to P and then substituting in PF. So the distance from A to D is the radius, but that is also the same as AP plus PF. Now, if I animate this, it's going to force this to move all over the place on this circle, and it's going to trace all of those values. And so it's forcing those distances to always be the same as that radius. And this is a beautiful picture of how planetary motion actually occurs, or maybe satellite. So you'll notice the acceleration and deceleration. So F in this case would be like the center of gravity, and point P might be the satellite or meteor that's actually traveling along. And so you notice at F, boom, it went very fast, and it's very, very slow as it gets to that furthest point. But then it gets faster and faster and faster as it gets, again, close to that center of gravity again. So there's a lot of reasons in planetary motion that these are used, but there's also a number of other more, simply applicable values where this happens. So just like in the previous problems, there was a certain form that just worked the best. And as it turns out, this is kind of the form that works the best. Is we'd like to have a perfect square over a number, another perfect square over a number, and it's equal to 1. And really, what this is x minus h squared. It is y minus k squared equals 1. And then I'm just going to use a and b for the moment, but it should look something like that. And we have to be a little bit careful about the way we talk about some of those pieces, because in this particular problem, this is correct, but in another problem, we have an issue. So the center of this problem is going to be at 1, 3, very much like what happened in the parabola. We're just going to find HK and we're good to go. So here's 1, 3. Love that. That's my center. Now, as it turns out, the vertices are going to be in the x direction, because this is the largest of the two, and the square root of 25, see, that's a squared, so the square root of that's going to be 5. I'm going to move over 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So notice that I went over and back 5, so that constant difference, that distance that we talked about, is 10. So somehow, every single time I do this problem, if I add those distances up, everywhere on this, I will get the number 10. Now, in the y direction, I'm going to move 4. 1, 2, 3, 4. 1, 2, 3, 4. Well, this is really kind of a pretty good place to go. Now we can actually sketch in our curve. We're just going to do the best that we can to make it look pretty good. And that is, you can see I'm in a little bit right here. I probably should have been a little bit fatter in that place, but you know, it's reasonably good. Now, those are my two vertices. Again, I started at 1, 3, and I went to the right 5, which got to 6, 3, and I went to the left 5, which is negative 4, 3. Now, this is interesting. Unlike the parabola where there's one focus, this one has two. So people call it either a foci, some people call it a foci. Heard it done both ways. It's all good. And all you have to do is you take these two values right here, which is a squared minus b squared, and notice it's minus, right? And that's going to be the square root of 9, which is 3. So along this major axis right here, I'm going to move over and back 1, 2, 3. So again, I'm kind of doing that on the line that connects those two vertices. So when I go over and back 3 from here, I got to 4, 3 and negative 2, 3. And these are my two foci. These are my two vertices. And these are called the end points of the major axis. Now, this problem is done, so don't worry about any of the rest of this that I'm going to do, but just for the sake of argument, if I took this plus this, I would get that number 10. If I took this distance plus this distance, I would also get 10. If I came over to here and I went over to here and I came back to here, that would also be 10. That's just the definition of what makes an ellipse work. Now, in number 2, I've changed the story a little bit because notice I like it to be equal to 1, and I kind of messed that up. So we're going to divide every single piece by 64. Now, that's going to give me x squared over 16 because I'm going to reduce, plus y plus 1 squared over 2 is equal to 1. So I can quickly see that my center is going to be at 0, negative 1. That's pretty good. It's right here. Now, again, this one is larger than this one, so it's definitely going to have its larger axis in the x direction. So I'm going to go over 1, 2, 3, 4, and 1, 2, 3, 4. So my vertices, V1 and V2, are at negative 4, negative 1, and 4, negative 1. And in the y direction, I'm going to go up and down. See, this 16 was 4. This is b squared, so b is going to be root 2. That's kind of ugly. So that's going to be here and here. So this is going to be, well, I guess I'm going to start at 0, comma, negative 1 plus root 2, and 0, comma, negative 1 minus root 2. That's kind of an ugly number, and I kind of did that on purpose, but square root of 2 is about 1.4 or something like that. So from up here, I went up about 1.4 and down about 1.4. So you'll notice that this ellipse is very much more exaggerated or eccentric than the previous one that I did. It's really wowed out a little bit. And now to find the foci, 16 minus 2 is 14. So my C value is what we call that is root 14. 16 minus 2 is 14. So I'm going to go to the center, which is 0, negative 1, and I'm going to move over and back root 14. But, you know, at root 14, let's see, what is root 14? It's about 3.7. So if I go over 1, 2, 3.7, whoa, it's way over here, really, really close to the edges. And that's why it's so eccentric. And we have a quick definition for that. So keep in mind, I told you that this is C, this is A right here. The definition of eccentricity is C over A, which is the distance to the focus divided by the distance to the vertex. And so in this case, root 14 divided by 4 is about 0.935. And it will always be a number below the number 1 because the vertex is always further away than the focus for an ellipse. When it goes above 1, it's going to be a very special shape called a hyperbola. And when it's equal to 1, it could either be a circle or it could be a parabola. So moving to our last one of these, number 3, we're going to do the same thing, but I had something special rigged up in this problem. I want it to be set equal to 1 like that last one, and I did something nice here, but over here something bad happened. And there's a little reminder of something that used to happen in basic math, is that every time you divide by a fraction, you flip-flop and multiply. So if you're multiplying by a fraction, it means you equivalently were dividing by that fraction. So this is 81 quarters. So keep in mind, if I divide by 81 quarters, that's like multiplying by 4 over 81. Now, that does lead us to a little bit of an issue. What is bigger between the two of these? Well, 81 quarters is larger than the number 9. I'm realizing that I made all of the x's bigger, and that is definitely not always the case. Sometimes the y value could be bigger, but this time it's not. So we're going to go to our center at negative 5, 3. That's right here. Negative 5, 3. There's my center. And in the y direction, I'm going to go up and down 1, 2, 3. 1, 2, 3. Those are the ends of the minor axis because this is the big dog. Now, this value, A, is going to be the square root of 9 over 81 quarters, which is 9 over 2. So that's 4.5. 2, 3, 4.5. 1, 2, 3, 4.5. Way out here. Again, slightly eccentric ellipse. Once we get that, we can usually kind of play connect the dots. So if we're over here at negative 5, and we move over and back 9 halves, excuse me, 3. So a better way to say that would just be called that maybe negative 5 plus 4 halves is negative 1/2 comma 3, which we can see right here, or negative 10 halves minus 9 halves is negative 19 halves comma 3. And last but not least, when we go for those foci, some of those numbers can get kind of bad. So again, what we're going to do is 81 quarters. We're going to take away that 9, and I got 11.25, or 45 quarters. So C is going to be the square root of 81 quarters minus 9, which is 45 quarters. And I'm going to try to simplify that a little bit. 45 is 9 times 5, so that's 3 roots of 5 over 2. Now, this is not a pretty answer, so I'm going to grab a decimal real quick. And I got 3.35. So if I go over 1, 2, 3.35, and 3.35, 1, 2, 3.35. And my foci, I didn't give myself enough room here, would start at negative 5. And I'd move over and back 3 roots of 5 over 2, comma, 3, because that portion never changes. And that is, again, the equation of that story. Now, again, the eccentricity, which the problem doesn't directly ask for, but I want you to get used to it, is E is the C value divided by the A value, which is 9/2. So, of course, I could kind of simplify that a little bit, and this would flip up and the 3's would cancel. So it would be 2 over 3, and it'd be the square root of 5. Oh, actually, these 2's could cancel, don't they? Let's go ahead and do that. So it looks to me like my eccentricity is root 5 over 3. Now, again, the closer that number is to the number 1, the more eccentric it is, or the more crazy it's going to look. And this one is a little bit crazy, but not as crazy as this one. And you can kind of see that in context of the picture, that this one is a little crazier looking than that one. Okay, so the next video, we'll split that up and look at what happens if somebody does not give it to you in the pretty form, and what happens if we simply describe it. So we'll be back for the next video shortly. Have a good one.